Yes. Okay. It's a pleasure to welcome Raul Carballo-Rubio today. He's currently at the Center of Gravity, the New Institute in Denmark, and also moving soon to the IIA in Granada, a place we all know and love very. And he'll tell us today, he's an expert on various aspects of classical and also some aspects of quantum gravity as well. He's interested so today actually he'll tell us about the meaning of infinity in black hole horizons and mass inflation. We're really excited for this talk. Raul was originally supposed to be here in person, but unfortunately he couldn't make it. But yeah, we'll see you in person sometime soon. Raul, take it away.
Thank you, Prashant, for the nice introduction, and also thank you also to Helen for the invitation to present this workshop, or to my work, sorry, in this seminar, in this series of seminars, the Black Hole Initiative Foundation seminar. I'm also grateful let me see, to my collaborators, my long-time collaborators, Francesco, who is a postdoc in Frankfurt in a group of Luciano Rezzola, Stefano Liberati at CISA, and Matt Visser at Victoria University of Wellington. Before I go forward, presenting the talk overview, is the sound okay? Can everyone hear me well? Also online, seems to be fine in the room. I also see the room, so let me know if you have any questions. You can raise your hand. I should be able to see that. And yeah, please interrupt me. Yeah, because it's different giving a talk in person or standing than sitting. So I think I would appreciate if there are interruptions and questions, because that way it will make it more engaging for everyone, I think. So the overview of the talk is, it's going to be divided in 4 sections. I'm going to start with some motivation. Then I will do a brief review of what we know about mass inflation for Cauchy horizons. It's going to be a very brief review in order to set up the stage for the discussion of mass inflation in the case of inner horizons. And I will wrap up with some conclusions. So I'm going to start with motivation. And starting with a simple situation in which we have the collapse of matter to form a core. And I'm calling it a core here because we know in general relativity that if we have a dense enough distribution of matter, it's going to collapse to form a singularity. But there's nowadays a lot of interest in situations that go beyond general relativity. That could be regular, could be physics because of quantum gravity effects. It could be because of modified gravity effects due to different situations. So then in this talk, I don't need to know what happens at the core. It could be singular, it could be regular, because I'm mostly going to be interested in the physics around the inner horizon, which is separated in most situations from the core. So that's why I'm not compromising I'm not focusing on any specific situation. So I just have matter collapsing to form a core that could be singular, could be regular, depending on the situation. And in general relativity, we know that the core is going to be singular. Again, if the matter that is collapsing is dense enough initially, and that is surrounded by an event horizon, which essentially is hiding the singularity from outside, so that we cannot see the singularity. So now what I want to highlight is that this event horizon it requires infinite time to be defined, and in particular, this boundary that you should be able to see, I think you can see the hand here in the slide, which is the line defining the event horizon, is essentially the first light ray that tries to escape from the distribution of matter that is collapsing, but that cannot escape in infinite time. So essentially, if I'm an observer that is seeing the collapse in real time from the outside, I will be able to see rays like this that are originated in the matter. They escape. Of course, there's curvature effects due to gravity, but eventually a ray like this is going to escape. And I will be able to see that from infinity. But at some point, when gravity becomes strong enough, this doesn't happen anymore, and there is a first light ray that is trapped, that cannot escape, and this defines the event horizon. In this figure, you can also see that there is a Cauchy horizon. The Cauchy horizon indicates the breakdown of predictability in this problem, in problem of collapse, and at least qualitatively, conceptually, a way of understanding this is that the Cauchy horizon arises because we have some repulsive effect. It could be in general relativity, it could be because we have a charge or we have rotation. So there's a repulsive effect that counteracts gravity at the core. It could also be quantum gravity effects or some, again, modification of gravity near the core. And essentially, the fact that we have this repulsive effect allows the possibility that there are some light rays that can stay in a finite region without reaching the core, reaching the singularity in general relativity, but also they are not able to escape because they are surrounded by an event horizon. So actually, if we focus on this light rays, and this can be done mathematically, one can see that essentially the exit from spacetime, or more properly, they reach the edge of spacetime in a finite value of the time parameter. And that essentially what implies the breakdown of predictability for which is associated with Cauchy horizon. So in realistic situations, we not only we would have perturbations, and I'm indicating them here with arrows. You can see some arrows indicating ingoing perturbations, and some other ones indicate outgoing perturbations. I'm just trying to be as general as possible, and then essentially I'm using Eddington-Finkelstein coordinates or generalized ones. That's because that explains the shape of the arrows. And when we have these perturbations, we know that event horizons are stable, while the Cauchy horizons are unstable. So they are kind of dual to each other, and we'll see that later in the talk, why that happens. And there are many works discussing this. I didn't have this is not a full list of references, but for instance, there are the works of by Price in the 70s about the decay of perturbations around event horizons, or the work by Ori about an exact mass inflation solution for Cauchy horizon. So as I was saying, so we need infinite time to define these notions of horizon, the event horizon and the Cauchy horizon. But we can also define other structures or other quantities or other objects in such a spacetime, which I'm going to be calling outer or inner horizons. But in the literature, you can find them more explicitly called future outer inner trapping horizons. But I will be just calling them outer inner horizons for simplicity. And this can be defined in finite time. So they arise, for instance, we can consider a simple situation of Oppenheimer's Snyder collapse in general relativity. In that case, if we monitor because we have the exact solution, we can see that at some point there's going to be a situation like this in which we create an outer horizon and an inner horizon. Now the outer horizon, if we continue to evolve the system, is going to eventually merge or be coincident with the event horizon in that solution, while the inner horizon is going to collapse, and at some point it's going to hit the singular core in the case of the Oppenheimer-Snyder solution. If we have charge, if we have rotation, if we have any repulsive effect, this inner horizon generically is going to stabilize, and it's going to be coincident with the Cauchy horizon if we wait for long enough times. So essentially, these are kind of finite time versions of the event horizons and Cauchy horizons. And just in the case of the future outer trapping horizon, the way of defining it would be the same way or a similar way as the event horizon, at least conceptually. But instead of focusing on light rays that can never escape, we can just ask the question about which rays cannot escape in a finite interval of time. That's essentially the idea which is behind the definition of such a horizon, which I'm going to discuss in more detail now. So just a quick detour of the mathematical definitions, in particular because I wanted to make sure that we understand the definitions of outer and inner trapping horizons. So the event horizon is the boundary of the causal past of future null infinity. Essentially, we just need to understand the causal past is the set of points that can affect causally some set. And here the set that we are focusing on is future null infinity. So essentially, this tells us that if we want to locate the event horizon in a given spacetime, we need to know where future null infinity lies and the properties that it has. And future null infinity in a asymptotically flat spacetime essentially implies infinite distance and infinite time. So essentially, we need to know the future, the complete evolution of our spacetime to determine where the event horizon is. And the Cauchy horizon has a different definition. It's defined in terms of a surface S, and essentially it's the difference between the closure of the future domain of dependence of the surface and the chronological past of this set. So essentially, we just need to take a surface and then understand which are the points that can be affected causally by the surface, and calculate the difference between these two sets. Again, this was just for completeness for these two notions, because I'm going to be working mostly with outer and inner horizons, but I just wanted to show the difference, like really both of them are based on different mathematical concepts. Because in the case of outer and inner trapping horizons, what we are going to define, or what we are going to need, is just to work with expansions of trajectories. So we are going to have a free surface H, and then we are going to define some scalar quantities on the surface. Well, we can define it all over spacetime, but we are going to ask that they have specific properties. And these scalars are these expansions, plus and minus, which are essentially the expansion of trajectories which are propagating along two null directions. So in a four-dimensional spacetime, it's always possible to define at each point two of these null directions, and I'm just going to call them plus and minus, or outgoing and ingoing. And essentially, this captures the idea that if I have four-dimensional spacetime and I have a sphere of light, the sphere of light can do two things: can either expand dynamically or can it contract. Essentially, it's following one of these two null directions, right? That would be the intuition in flat spacetime, but if we have a black hole, then the situation can be different. This is what is captured by this definition. So essentially, we can just calculate these quantities, these two expansions, plus and minus, and then the outer or inner horizon is going to be defined by the outgoing expansion vanishing on it, while the negative expansion, the minus expansion, is negative. So essentially, this captures the idea that light rays, that ingoing ones, they can just cross, go through the horizon, while the outgoing ones, they are trapped. They cannot really escape. And now I can define, yes.
So as A increases, as the spin of the black hole increases, the Cauchy horizon approaches the event horizon. And in the limit of n equals 1, it is coincident with the event horizon. That's right?
Yeah, in the extreme situation.
The Cauchy horizon is unstable against perturbations of spacetime. Does that mean anything that happens that would disturb the spacetime, a gravity wave, a particle, somebody throwing their shoe in the black hole, anything like that would collapse the Cauchy horizon? What is it unstable against, and where does it go when it is destabilized?
Yeah, so in order to answer that question, we need to have specific dynamical equations, right? And in general relativity, in particular, so it's well understood that something is going to diverge, and essentially curvature invariants are going to diverge. Also, some definitions of local, quasi-local mass and energy are going to be divergent. But it's not clear what the general outcome of this evolution is. So because it could be expected to be a singularity, but it could be a singularity with different degrees of it could be more or less singular, let's say, because it could be extendable, for instance, or it can be an integrable singularity. It can also have it can be time-like, it can be space-like, depending on the situation. So it's not really clear what the outcome is. But the idea is that an observer if we don't have perturbations, an observer wouldn't see anything special in principle at this horizon, right? But as soon as we add perturbations, there is something that the observer is going to see the blow up of some physical quantity. It can be mass energy, it can be curvature, and then whether or not the observer can in some way go through, we can define an extension mathematically. It's an open question. I don't know if that answers the question.
Thank you.
I also have a question.
Yes.
So, Cauchy horizon, you said there are outgoing rays, but they are trapped, right? They can't come back into our universe. But when you look at all these maximally extended Penrose diagrams, they do escape, right? They go to another universe.
Yeah.
How does that tie into all this?
Yeah, so essentially this is that connects with what I was saying, that these rays essentially reach the edge of spacetime, right? And then when we extend them, that's when they can continue and go to another universe, right? Essentially, it's because within the domain of dependence of the original Cauchy surface, these rays, we don't know how to continue them, right? They reach the Cauchy horizon, and then it's a matter of extending them. Once we extend them, is when generically you will have different asymptotic regions, a different universe if you want, and this is where these rays go. But this information is a mathematical process, right? It's not within the domain of dependence on the original problem.
I see, okay.
Any other questions? Doesn't seem to be the case. So yeah. So coming back to the definition of the of the expansion, well, of the inner, outer and inner trapping horizons. So as I was saying, this is defined by the outgoing expansion vanishing, which is this quantity here, this equation here, while the ingoing expansion has a negative sign. And now we can have two types of horizons depending on if the sign, well, the change, if the positive, the outgoing expansion changes sign from positive to negative or to negative to positive. Essentially, this is what is controlled by the d derivative along the ingoing direction. This quantity, if it's negative, we have an outer horizon. And if it's positive, we have an inner horizon. And again, we can see that we are really using different mathematical elements to define this because the expansion can be defined quasi-locally. It just realized this definition, the expansion of along two null directions, and this is what we can use in order to define this horizon. So essentially, if we are in a situation in which we are doing finite time measurements, or we are just working with finite time concepts, we cannot know if the placement, if there are event or Cauchy horizons and where they are going to be placed, if we don't have the full information of spacetime, but we can still define these outer inner horizons. And the way of doing that would be, as I was saying before, essentially we just need to calculate the expansions around two null directions. And the situation that we would see if we do a slicing like the one in the figure here is that both expansions, the ingoing expansion is always negative on this direction, but the outgoing expansion, if I'm outside, it's going to be positive. Here it changes sign to negative to be negative in the green, in this green set. And at some point, it's going to change sign again to become positive near the core. And this is something that I can measure locally so that I can identify where this structure is. Now, even if we don't understand, or we cannot really locate the event horizon or Cauchy horizon in this picture, we know that these objects, if they exist, they are going to be, as I was saying, stable or unstable, stable for the event horizon, unstable for the Cauchy horizon. And is it reasonable, at least it seems reasonable to me, to expect that there exist some type of finite time versions of the theorems of these theorems of stability and instability, which apply to a situation like this, just because of continuity. Because in principle, if I can do this, let's say, experiment, or I can consider the situation for different intervals of finite time, and I know that if I allow the system to evolve infinitely until infinite time, so that it has event and Cauchy horizons, I know that the Cauchy horizon is going to be unstable. So I would expect to be able to see this continuously, so that I don't have to wait for an infinite time to see this. Of course, this is even more important because we expect that due to physics beyond general relativity, we may not even have event horizons and Cauchy horizons. For instance, let's take Hawking radiation, because we have evaporation. Just on the basis of that, it's questionable that we will have event horizons. So that implies that maybe the situation that is more interesting mathematically to analyze is a situation in which we form these outer and inner horizons. They exist for a very long time. At some point, they disappear. It's a completely different topic that I'm not going to enter in this talk, like how these situations can mimic the properties of a situation in which we have event horizons, right? And what are the differences between them? What I want to highlight here is that in this case, in a situation like this one, we really don't have Cauchy horizons or event horizons. So that implies that we cannot really use the theorems that we have for the situations. We cannot really argue that this horizon, the outer horizon, is stable, or that the inner horizon is unstable, unless we have finite time versions of these theorems. And if developing those, then we would be able to essentially gain some intuition about the situations. And that's the motivation that I'm going to be focusing on or following, in particular for the case of Cauchy horizons, inner horizons, just to try to see if we can extend the instability of Cauchy horizons to inner horizons. So before I continue, are there any questions? Okay. So I'm going to review in one slide the results for mass inflations for Cauchy horizons. So I'm going to be focusing on the situation in which we have, I'm going to be forgetting for the moment about the future, like inner and outer horizons, and then just going to be consider a situation in which we have an event horizon and a Cauchy horizon in particular, which is the focus now in this slide. And we are going to have perturbations, which are ingoing perturbations, outgoing perturbations. You can see them here. Actually, there is a very nice exact mass inflation solution found by Ori in the early 90s, in which that this exact solution, we need, in order to find it, we need to have a very specific matter content, which is going to be an ingoing stream of radiation. So essentially, there is a continuous flux of radiation. And there is also an outgoing null shell. So essentially, there is a source, a matter source that is distributional. There is a delta source here along an outgoing trajectory. And we know how to deal with distributional sources in general relativity. Essentially, the key issue is solving junction conditions along the outgoing null shell. Essentially, we just need to glue two geometries along this outgoing shell, which again, technically is well understood how to do. And the result that in this paper, in the early 90s paper, is that one can calculate the Meissner sharp mass in the shaded area, in the blue area here, and show that it diverges exponentially at late times. So essentially, it implies the Meissner sharp mass here is the mass that is enclosed by this outgoing shell. So they have a shell that is outgoing. Of course, even if it's outgoing because of the gravitational field, it cannot really escape because we are inside a black hole. That's why it's approaching the core. And I can monitor the mass and energy inside the shell, in the region enclosed by the shell. This quantity is going to diverge exponentially at late times. That was the content of the exact solution found by Ori. And so we are going to derive later this as a particular case so I'm not going to go into more details, mathematical details right now. So the thing that I wanted to discuss now, or I wanted actually to open a discussion about whether or not the divergence is necessary or how important it is in this case. Because as I said, this definition is that there is an exponential divergence in the mass, and this is what is conventionally defined as mass inflation. So before I give you my biased opinion on this, I wanted to get to know if there are any thoughts in the audience about this, how important is the divergence, and if there are any differing opinions, we can talk about this. So feel free to raise any concerns or any comments that you may have on this. Like how important is the divergence in this business?
It's not a question. So when you say that the mass diverges, it means that the mass of the black hole, the mass of the core is increasing exponentially. Is that what you're saying?
Mm-hmm. Yes. So are there any other comments or like suggestions about how important is the fact that we have a divergence, an infinite there?
Sounds like an issue.
I just wanted to give some time. So just to see if there are any comments.
I have a question. So in all of
Okay.
these,
Yeah.
in all of these cases, you don't have any change in the Meissner sharp mass outside of the Cauchy horizon, right? Or let's say sufficiently outside the Cauchy horizon. There's nothing really changed. Is that right? It's only from the Cauchy horizon onwards.
No, it's outside. So it's it's outside. Actually, the shaded region should include the Cauchy horizon. Actually, so here, so it should be cut here. So this is the region where the statement applies. Actually, so it's.
So would you say outside the event horizon there would be no change in the Hawking mass or the Meissner sharp mass, etc.?
Yeah.
Just inside
Exactly.
the.
Yeah. So essentially, if one considers the same setup, which is I have an outgoing, I have ingoing matter here, I can calculate the same thing. Essentially, just the kind of like this blue area is going to be here around the event horizon, right? In that case, I wouldn't see an exponential divergence. I would actually see something that is, you don't see any increase beyond the usual balance of energy between the ingoing and outgoing matter that you have. It's only when you are inside and only when you are next to the Cauchy when you see this exponential behavior.
So there must be some region inside the outer horizon where also you don't have mass inflation, right? Maybe if you have to be sufficiently deep inside the outer horizon to then start seeing mass inflation.
You need to be sufficiently deep into it. Yes. That's why this result by Ori is valid at late times, because you can do the argument by a shell. So, but you need to wait for long enough so that the shell really gets close to the Cauchy horizon for mass inflation to be there. So, because essentially, but there you are just letting the system approach dynamic, right? Because you're just letting the shell approach to be close enough. And in that case, but we can see, I will show later numerically, because one can see how quickly this happens and how close you need to be to the inner horizon. So you can play with this and see this explicitly. Okay, so then I will continue giving my perspective on this issue of the whether or not the divergence is necessary. And the perspective that I'm going to be following this talk is that in most situations, of course, mathematically it makes a difference to have something divergent or not, because mathematically it's different to have a function that is divergent as something compared to a function that is bounded, right? Even if it has a very large value. But physically, in most situations, they are going to be indistinguishable, because physically we'll always do experiments in a finite amount of time, right? So we cannot really keep track of something that is divergent, because we'll only be able to see it increasing up to a certain value. And also there are the issues that the effective theories that we use at some point are going to cease to be valid at some energy scale if things keep growing up. So for me, the motivation here is that infinity, when we have a result like this, like in the case of Ori, in which we have something that is infinite, is a motivation to try to find results that are going to be, well, both results and definitions that are more physical, and that allow us to essentially have the same ingredients and see similar physical phenomena, but without requiring the notion of infinity for the formulation. And that's I'm going to be focusing in the next slides, essentially just discussing the generalization of this picture, but instead of having Cauchy horizons, having inner horizons. So I'll move to discuss that situation. So the diagram in this case that we're going to have is a very different one, meaning that we will have outer and inner horizons, but we will not have event or Cauchy horizons. So we change the situation. We lose this structure, this mathematical structure that we had, the one of event and Cauchy horizon. They are no longer there in a spacetime like this one by construction. And we want to understand if we have something similar to mass inflation here. Of course, we know that if we take the infinite time limit in this diagram, essentially make it infinitely long, we'll recover a situation with Cauchy horizon and event horizons in the limiting case. So, but we want to stay within the finite time situation and understand what happens with mass inflation. So I'm just gonna go into the mathematical details of a situation like this one. We can, for spherical symmetric situations, we can analyze it using generalized Eddington-Finkelstein coordinates, in which we have two functions, this function phi and this function f. This is the freedom that we have in geometric terms. The function phi is not going to be really that important. And actually, in the specific examples that I'm going to discuss, I'm going to consider that it vanishes. If it doesn't vanish, it's going to change some results quantitatively, but not qualitatively, because the qualitative physics is controlled by this function f, because it also controls the location of the inner horizon and the outer horizon. Because if one calculates the expansion of outgoing and ingoing geodesics, as I was explaining, that needs to be done for the definition of these horizons, then one can see that these the outer and inner horizons, they appear whenever the function f vanishes. So that if we have a situation like this one, in which I have an outer horizon and an inner horizon, then I'm going to have 2 points in which this function vanishes. We can imagine that we have a constant slice of time, like the one that I was drawing before. So we have 2 points in which the function vanishes. One of them is going to indicate the position of the outer horizon. The other 0 of the function, is going to indicate the position of the inner horizon. And this can be function of time, because we can see that in this diagram is changing in time. So the position of the inner horizon is changing and the position of the outer horizon is changing. So we essentially have a situation in which we can have these horizons can be created, they can change the position, they can grow, they can shrink depending on the situation, and they can at some point disappear. So all that is included in a function like this one, well, a metric like this one. And in the setup, we can calculate the Misner sharp mass. which essentially is going to be the inverse of the GRR component of the metric. Well, as the RR component of the inverse metric, sorry. And just conceptually, the important thing to keep in mind is that this describes it's the Misner mass is a function of time and the radius. And the meaning of these two variables is that it tells us the mass and energy that is enclosed in a sphere with radius r at a given moment of time. So essentially, if I fix the radius and I keep moving time, I'm just asking like for a sphere with fixed radius, how is the energy and matter changing in time, right? And the opposite. So essentially, these are the two variables, and this is the main quantity that we are going to be calculating numerically. We will calculate this inside the outgoing shell. That will give more details later about that. So this is the geometric setup that we are going to use. Eddington-Finkelstein coordinates with a function that has two zeros because we have two horizons, and they can be time dependent so that we are able to accommodate general situations. So now in this setup, we can calculate, or we will need to calculate the equations for outgoing null geodesics, which for the metric is given by this simple expression, essentially a generalization of the usual equation in Eddington-Finkelstein coordinates. And in particular, for the situations we want to analyze, or for the analysis that we are going to do, it's useful to do an expansion around the position of the inner horizon. So we don't really need to keep track of the whole evolution of the outgoing geodesic, which is here, but we can just do an expansion to cover an open set around the position of the inner horizon. So we can just do an expansion of first order, in which essentially we just have a Taylor expansion, and we're evaluating it in the position of the inner horizon, which is quantity here. And we can essentially just write this expression as a differential equation for the difference between the radius of the outgoing geodesic and the position of the inner horizon as a function of time. The first order is going to depend on the surface gravity of the inner horizon that we have defined in this way. Essentially, this is a definition that is equivalent in stationary situations to the usual definition of the surface gravity in an inner horizon. And this quantity is going to depend on time, in this case, in general situations, and is generally negative for inner horizons. Actually, if we consider the equivalent definition for an outer horizon, it will be positive. So essentially, this is related to this thing that we were discussing, and there was this question about why we get mass inflation near the inner horizon, and we don't see this in the outer horizon, essentially coming from the different signs of this quantity, as we will see more explicitly. But we have this differential equation that tells us it's just a differential equation that tells us how the outgoing geodesic is approaching the inner horizon as a function of the surface gravity, and also as a function of how the inner horizon is changing in time. So of course, in stationary situations, we don't have any change in the position of the inner horizon. We don't have any time dependence, so we wouldn't have this term here, which is the derivative of the position of the inner horizon. We also don't have any time dependence here, and we also don't have any time dependence in the surface gravity. So this equation, we can integrate that in a stationary situation, and we just get an exponential behavior that tells us that the outgoing trajectory is going to approach exponentially the position of the inner horizon. That doesn't change. And this result, this exponential behavior, is essentially we can just trace back mass inflation, the analytical result of mass inflation in late times, to this result. The fact that we have an exponential behavior in this geodesic, in this outgoing geodesic equation, is related to the fact that we observe an exponential mass inflation. As I was saying before, the fact that we have a negative surface gravity around inner horizons, it what makes this exponential be growing in the case of inner horizons for mass inflation, while in the case of outer horizon, it's no longer the case. So of course, that's for stationary situations. We want to cover more general situations in which we will have generally these terms. And within all the possible general situations that we can consider, there are situations in which the exponential behavior, while it's not exact, it's a good approximation. And those are the situations in which two adiabatic conditions are satisfied. So the first one is that this term here that vanishes identically for stationary situations, it doesn't vanish, but it's small enough so that we can essentially ignore it. And this happens when we have this inequality here. This term The second term is way smaller than the first term. The second adiabatic condition is essentially that the surface gravity doesn't change much in time. So it changes slowly. And that allows us, if we have the two conditions, essentially we have an exponential, an approximately exponential behavior controlled by the surface gravity that is changing slowly in time. That's why the adiabatic condition. So now even if we have the second adiabatic condition being satisfied, the first adiabatic condition is always going to cease to be valid, as you can see from the equation, because if both adiabatic conditions are satisfied, we have an exponential approach to the inner horizon. And this implies that this quantity is going to decrease exponentially. And at some point, this inequality, that implies that the inner horizon, the variation of the inner horizon is small enough compared to this, to the surface gravity multiplied by the difference between the position of the outgoing trajectory and the inner horizon. So this inequality doesn't really, it's not going to be possible to be satisfied generically, unless we have asymptotic stationary situation, right? So, which means that if this quantity vanishes asymptotically, then it can still be satisfied. But if we have a generically dynamical situation, this condition is not going to be satisfied. So that tells us that mass inflation in this situation is going to be bounded by a maximum value. And we are going to see this numerically later. It's just that analytically, one can understand that this is going to be the case when, just because of this. So this is about the adiabatic conditions. We will see them explicitly in more detail later as well when understanding a specific setup. Because now that we have, so we have understood how the outgoing geodesic displaces, moves. We have done a perturbative expansion around the position of the inner horizon. And now if we want to do,
Previous slide.
Yes.
So I think what you're saying is there will be an exponential infall. R minus R in will decrease exponentially. And then it starts hovering once it violates the first adiabatic condition. Is that what basically happens? It doesn't keep on going exponentially, but just kind of sits around the place where this is violated.
Well, it actually crosses because in an exponential approach, it's not possible to cross the inner horizon, right? But if we have a dynamical situation, what is going to happen generically, well, there can be different situations, but at least the ones that I'm going to be discussing, is that the outgoing shell actually crosses the inner horizon. And that cannot be captured in the exponential approximation, right? That's why it breaks down.
It's not hovering, but actually accelerating and going through. Oh,
yeah, going through, exactly.
Very okay.
Any other questions? Okay. So yeah, we can, in order to proceed, because this can be done analytically or what can be understood analytically of the geodesics, but now I would like to, I mean, it's nice to see, just going to show some numerical results that allow us to understand what happens in this whole evolution region, essentially. And for that, we need to specify a model. We just need to specify essentially a space-time, specific space-time that has this structure, that has an outer horizon, inner horizon, and is changing in time, right? That's essentially what we need to do. So we can pick many different space-times. I'm going to focus for concreteness in the what is called the Hayward space-time, which is a particular regular black hole space-time. But we could consider, for instance, a charged black hole. But in this case, the good thing about this space-time is that it's regular, it doesn't have any singularity. And this is possible because we have a new physics scale, which is this L parameter that you can see here, that is regularizing, is essentially providing an upper bound for the curvature in this spacetime. As you can see, this is a deformation of the Schwarzschild metric. So if we make this new parameter scale vanish, new physics scale, if we consider it vanishes, we recover the Schwarzschild solution with a deformation of it. Well, actually, it's not a deformation of Schwarzschild because we have a time dependence here as well, right? So it's actually, technically, it's a deformation of the Vidia solution because we have a function that depends on P. So as I was saying, the function phi, we can consider it vanishes. We can also, when we have done different types of calculations, different situations, including non-zero vanishing values of phi, and we understand that it only changes qualitatively. We can discuss this at the end of the talk if you would like to understand that. But the simple situation is just to make it vanish. And in this metric, we understand that we have the new physics scale, right? That we are going to be talking about it in more detail later, or will be important for some of the arguments. And then we have these two functions. We have the function m of b, right? And we have a plus minus. The plus minus sign implies it's coming from the fact that we have an outgoing null shell. As I was saying, this is a distributional source. It's a delta source that is singular there. And we are just, it implies that we have two spacetimes, the minus spacetime, which is outside of the shell, and the plus spacetime, which is inside, as you can see here. And we are going to glue these two spacetimes around this outgoing shell. Okay? So that's why we have a plus minus sign. But we have two copies of the same spacetime with just different functions. The function m minus is the bonding mass along path null infinity. Essentially, it tells us how the asymptotic mass of the black hole changes in time. That's the condition, or the information is m minus. And we are going to fix this. And for this geometry, if we consider different values of time or different values of this bonding mass, then we can have different situations. We can either have no horizons, we can have an extremal horizons, or we can have two outer horizons. This just comes from the fact that we can understand this is a polynomial, essentially, like f vanishing is a polynomial on the radius that also with coefficients that depend on the mass, and depending on the value of the mass, then we can have this situation. A situation with no horizons would be a slice of time like this one, in which we are not cutting this region. The situation with extremal horizons, we're just cutting the edge, we're just touching the edge of this region. And the situation with two horizons, we are just cutting this region, and then we have two horizons. So this is the information that is encoded in this geometry. And as I said, the m minus function is going to be fixed. It's a asymptotic mass of the black hole, and we are going to fix it. And, while the internal mass function, m plus, is completely fixed by the junction conditions and along this outgoing shell. So the radius of this outgoing shell, I'm going to call it capital R as a function of B. So this internal mass, m plus, is completely fixed by these junction conditions. There is not more freedom in the geometry. If you want to think about it that way, it's essentially fixed by energy conservation. Because if we want energy to be conserved on the shell, then the internal mass is fixed. And actually, we can use, in terms of, both things are equivalent. And when we were doing the numerical simulations, we were checking both using m plus, or using the Misner-Sharp mass as the variable to be integrated, and both of them are equivalent. But because the Misner-Sharp mass has a physical interpretation as the mass energy enclosed by this outgoing shell, I'm going to be using that one. This is, I think, it's the preferred choice. But you can see that both of them are related by just a simple transformation. So essentially, we can just write the Misner-Sharp mass evaluated on the outgoing shell as a function of m plus, and the opposite. So we can essentially change variables. So it's possible to use any of them. But I will be focusing on the Misner-Sharp mass. Essentially, I will be using the junction conditions to understand how this Misner-Sharp mass changes in time. And again, just a reminder that this is just the mass that is mass energy enclosed by the outgoing shell as the shell is changing in time. So that's essentially what this mass is encoded. And the value of this mass is fixed by junction conditions, as I was saying, just essentially energy conservation. And for this form of the metric, the junction conditions are very simple. They essentially take the form of 1 over f, df dv, the derivative of f with respect to v, has to be equal on both sides of the shell. Essentially, we calculate this quantity on the plus geometry, we calculate this quantity in the minus geometry, we evaluate it along the radius of the outgoing shell, and this quantity needs to be the same. It's something that can be obtained mathematically, and this is the equation that we can integrate numerically to obtain the Misner-Sharp mass on the plus region, which is essentially the interior mass inside the shell. So the last ingredient that we need in order to be able to integrate this equation is to fix the shape of this region, because we have fixed the fact that it's going to have a specific profile in this function f, the Hayward metric, but we need to fix like the time dependence of this region. And again, like none of the results really change when doing this. We have considered different situations, the same way that we were considering different geometries, like the alternatives to the Hayward geometry. as long as you have a situation like the one in the figure, which is you form some horizons before an initial time or around an initial time vi, then the horizons stay there for an interval of time until they disappear at VF, and then you have the adiabatic conditions being satisfied here. Essentially, in all the situations, you're going to see the same result, which is going to be some exponential growth of the mass that I'm going to show in the next slide. But for concreteness, again, this is just for the perspective of model building. In order to do a calculation, we just need to have a specific model that is encapsulating this behavior. And this is the type of function that we would have. Like as I said, this is the bonding mass, the asymptotic mass of the black hole, minus. It would have a background, which is just a black hole that is created at a certain moment and disappears at a certain moment afterwards with a maximum mass, which is going to be reached at some point in the middle of this evolution, which is m naught. So this is what is encapsulated in the background. And then on top of this, we have some perturbations, which is going to be this ingoing perturbation coming into the black hole. This is the delta m. And then we have an interpolated function, which essentially goes from 0 to 1. And is the one that is switching off the horizons and switching them on around VI. That's why it depends on VI. And then it's switching them off after VF. And again, depending on the interpolation function that we use, this transition can be more or less sharp, both around VI and VF. There can be different implementations. This function can be of compact support, but in the case that I'm going to be discussing, we are going to be using hyperbolic tangents, and essentially it's a function that vanishes before VI or will before VI. Then around VI it takes like order 1 value, then it gets a maximum value around the middle of the evolution, and then it goes back to 0 smoothly after the evolution. So essentially this is just a function that is telling us that initially we don't have a black hole. At some point we form, well, we don't have horizons. Then afterwards we form the two horizons, and then at some point we make them disappear. Right? And again, the values of the parameters, they're just controlling all the possible, like the total time scale, which is VF minus VI, how sharp this transition is, and none of this is really going to affect the main result that I'm going to be discussing. So now with these ingredients, we can go back to understanding what the adiabatic conditions. Yes.
I have a question on the previous couple
Yes.
slides, I guess. So you specified the shape, the radius of the outgoing shell, right? That was R of V. But are you also going to specify what the energy density is on that shell, or the stressors on the shell? Because you do show the m plus and m minus. So what are you choosing for what is on the shell, which will determine m plus for you, or like m minus for you, whatever whichever you're choosing?
Yeah. So it's just it's a null shell, so that is following a null trajectory with just energy density, so with no pressure.
Okay, I see.
So it's kind of like the simplest thing to.
Thanks.
And of course, like these are initial conditions for the integration. So I'm going to show, because I'm going to be showing integrations in terms of the initial value of the position of the shell and also the initial mass. But as long as the initial radius is inside the region of the two horizons and you have a positive energy density, like the results are going to be the same. Of course, there is some variations about the time scale in which this happens and like the onset of mass inflation, but yeah, essentially there is robustness like for these changes. Yeah, so in order to understand what the adiabatic conditions are telling us, we can just do a few manipulations of the adiabatic conditions, which essentially is like in the previous slide. Remember that we have essentially two scales in the problem. We have the new physics scale, and we have this maximum mass of the black hole, which is kind of like the macroscopic mass of the black hole. So we can use these scales in order to really understand what is the meaning of the adiabatic conditions, right? To at least do it in a conceptual or in a simplified way. M naught is proportional, like m minus is proportional to m naught, so we can use them. We can just use them equivalent to them. So if I take like the higher world black hole, or also any other regular black hole, generically we have this following these relationships that I'm showing here. Essentially, the position of the inner horizon is given by this new physics scale plus corrections that go as powers of the new physics scale divided by the mass of the black hole, while the surface gravity is minus, well, 1 over L, 1 over the new physics scale. And again, I have polynomial corrections to it. And there is a minus sign here, just because the surface gravity of the inner horizon is negative. Just remember that. So just if we plug this into the adiabatic conditions, actually the second one, we just have a condition on the perturbations. So essentially it tells us that the variation of the perturbations in the black hole, they have to be way smaller than this dimensionless coefficient here, which is the mass of the black hole squared, maximum mass, divided by the square. And this is essentially the two scales that we have in the problem. And this is essentially a constraint on the amplitude and the variation timescale of the perturbations that we put on top of the black hole. So now if we're considering perturbations, it's natural to assume that the amplitude of these perturbations are going to be way smaller than the mass of the black hole, right? To have something that is really perturbative. So then that means that we are left with a sufficient condition on the variability or the variation of the perturbations, which essentially it has to be greater. Look, they have to change in a slow enough way where the time scale is controlled by this L squared, the new physics parameter squared, divided by the mass of the black hole. So now if we take a look into, if we just think about the values that this constraint can take, it's actually a weak constraint all over, over the possible situations that we can think about. An obvious situation would be to consider that we have a regular black hole with regularization parameter, which is the Planck scale, right? In that case, essentially this, we know that the new physics scale compared to the mass, for instance, for a stellar mass black hole would be like 10 to the minus 38. So we can see that this really is a very small number, right, for that particular case. Of course, the constraint is going to change depending on the position of the radius of the inner horizon, or this new physics scale, if you want to say it that way. But this is still a weak constraint, even if we consider this the two scales are the same, like order 1. Because in that case, it essentially is telling us that the perturbations need to change slow enough compared to the mass of the black hole, which is still a reasonable constraint to consider. So in fact, that's the information on the constraints that we have on the accretion profile, which is a delta time. So I had here a slide to discuss a bit more what this means. Just because previous analysis of mass inflation, they were focusing on accretion profiles, functions delta m, which were decaying polynomially. And that's coming from Price law, from the fact that if we have a black hole that is formed, and eventually we know that it's going to decay eventually at late times polynomially. But we don't know if, that's for a black hole that is formed in vacuum, right? So we don't have any more, for instance, we don't have an accretion disk around the black hole. So because of the analysis of the condition we were doing, we know that we can actually consider more general profiles. So really the polynomial decay is not important for mass inflation. It was understandable as an element in the analysis of the late time evolution, but we really don't need it. And actually we can consider very general accretion profiles. As long as the accretion profiles change slowly enough, then we will still have mass inflation. And we are going to see this explicitly. For instance, something that is very simple, the simplest illustrative example of this would be, instead of having a polynomial decay, which would be the Price law. So the Price law would be the expression with epsilon equals to 0. So we essentially have an amplitude divided by the time v to a certain power. That's the content of the Price law. We can superimpose an oscillatory behavior on top of the Price law with some amplitude and some frequency, right? And this is kind of like a toy model to say, okay, what would happen if instead of having something polynomial, I have something that oscillates, and I can just change how quickly it oscillates, right? From the adiabatic conditions before, we know that mass inflation doesn't really require a specific profile, like a polynomial profile, anything like that, but just requires long enough variation timescale. So essentially, we have a timescale that is set by the problem, which is by the new physics scale and the mass of the black hole, and then I have perturbations that can be, again, depending on the physical situations that we have in mind, they can change very rapidly. They can have a series of features that we may need to model in different ways. But again, as long as these changes are slow enough compared to this timescale, we expect to see an exponential behavior. And this is what we see numerically. So I'm showing this slide. Again, I'm just putting everything together, and I will explain like the different parameters and how this is done. Again, I'm just considering the perturbation profile, which is this ingoing perturbation that is following this simple law, which is a polynomial law modulated by an oscillatory behavior, as the simplest toy model one can consider to see how changes in the polynomial law change the situation. And I'm going to consider a mass of the black hole, which is 10 in the units that we're using for the integration, and the new physics scale is 1. So there is essentially just separation of scale, which is of 1 order of magnitude, which is the minimum that you could have in order to have separation of scales. Then we'll have the initial formation time is -20, the disappearance time if the horizons would be 1000. So you can see that there is, in the units being used, this is long enough. It's enough time for this to for the two horizons to be there. And then there are some parameters that, again, remember that they were just specifying how quickly the transition from having no horizons to having horizons are. For the shell that we are considering, we consider a shell placed at a certain time, certain value of the radius, which is inside the inner horizon. This is essentially 5 in the units that we are considering. And the results that we see are the following. So if we don't have any oscillation, so we just have polynomial law, then we see that initially we don't have so because we don't have a black hole, so we don't have any change in the Misner-Sharp mass. But at some point, because of the initial conditions that we selected, then the mass inflation is gonna start appearing, right? So we are going to have an exponential behavior of the Misner-Sharp mass that is going to continue until at some point it's going to saturate. And the saturation is, as the question by Ramesh was pointing to, is coming from the fact that the outgoing shell at some point is going to exit this region. Essentially, this mass inflation can happen from the point at which we have perturbations until at some point when we have changed the condition of the system and the outgoing shell exits, then we can no longer see it, or it does no longer happen. So this is what we can see numerically. So essentially, as you can see, so of course, depending on the initial conditions for the shell, the outgoing, like the time in which the maximum mass is going to be different, because there could be different shells are going to exit the trap region at different times. But this behavior is universal for any shell, again, with a positive energy density. There is a mass inflation period, which we expected because of the adiabatic conditions being satisfied, until a certain mass is reached exponentially, which in this case, you can see that it's controlled again by the two scales that we have in the problem, and it's a large quantity. So if we switch on the oscillatory behavior so that we have some oscillation, what we are going to see is just a modulation of this exponential behavior. So essentially, this is the purple line, the dash one. We still have, on average, the exponential behavior, but it's going to be modulated by the oscillatory behavior. And that's what we expect to have in realistic situations. When we have realistic situations in which we have, imagine that this accretion could be like coming from an accretion disk. Of course, it's not going to satisfy an oscillatory behavior. It's going to have a more complicated behavior. But as long as the timescale is larger than the timescale set by the timescale variation of mass inflation, then we'll see something that on average goes exponentially, and there is going to be, the variation is going to be superimposed on top of it. That's what we expect based on this model, and what can be checked explicitly as well. So this is about the result. Yes.
So you're looking at a finite time, right? You told us in the beginning, you're not going to go to infinity. You're going to look at what you can observe at a finite time.
Mm-hmm.
You're looking at the formation of a black hole, right? You form this outer and inner horizon. That's at the bottom, and the green area is the region between horizons.
Yes.
Then you've got this top pinching off, right? The black hole disappears, or at least the horizons disappear. Is that always guaranteed, or is it only a feature of particular model you picked?
Mm-hmm.
Can these guys just keep on continuing without closing? Because then the story is different.
For evaporation. the late stage.
Yeah, so that's built in the model. Just because if they don't close, right? If these two horizons don't meet, then we are in a situation in which we will have eventually a Cauchy horizon, right, and an event horizon, and we know what would happen in that situation. So let's say that we took the situation that is the most different one to what we know, right? So because if we make them close, then we don't have these structures, but we can still see that even in this situation, which is different, we still have the same, well, a similar phenomenon for mass inflation, right? But the answer is, yeah, it's built in. So we are choosing a geometry that is doing that just because it's the most different one, the one that shows a more dramatic difference with respect to the ones that we have under control.
Thank you.
So the motivation here for it closing off is evaporation, right? At the end?
Yeah.
Yeah.
That's the original picture.
Yeah.
That is Hawking radiation and all that. But this is a nice toy model. So I was just wondering what is necessary and what is a choice. So this closing off is a choice that you made.
Yeah, it's a geometric choice for the background, so we are considering. Essentially, what would happen if this doesn't close, the analysis is still, like, we can still use the same, because, I mean, the same techniques can be applied. The only difference would be that if this doesn't close, then this exponential behavior is going to continue indefinitely. It's just going to continue. Essentially, is the difference. If we close the region, then at some point it's going to stop. If we don't close the trapped region, then it's going to continue building up until it diverges, and thus we recover the usual results for Cauchy horizon.
I have another question, but maybe if you finish, then I can ask you that as well. We're on time.
Okay, it's up to you. I mean, it depends if it's related to this. Maybe it's better to have it now.
Yeah, I'll maybe ask after you finish. Please go ahead.
Okay, sounds good. Yeah. Well, I'm actually about to wrap up. I mean, just gonna discuss some implications and some conclusions. So and again, we can just come back to the details that you would like to understand better in the questions. So just a reminder that inner horizons, which is the main ingredient on all the in the developments on the mathematics that I've been discussing, right? Like we need to have an inner horizon in order to understand or to have mass inflation. So they are generic, so they appear like in general relativity, they appear, of course, the charge situation is we don't expect to be astrophysically relevant, but rotation we expect to be there in astrophysical situations. But also, even if we didn't have rotation, if we have some type of singularity regularization due to quantum gravity effect or some modified gravity effect, we are going to have inner horizon. So it seems to be inescapable to deal with inner horizons. On the other hand, we have discussed that once we have inner horizons, regardless of whether or not they are Cauchy horizons, we are going to have mass inflation for accreting conditions which are astrophysically reasonable. And mass inflation in this case is defined as an exponential behavior of the internal mass, which is modulated by the accretion profile. So on average, we have an exponential growth, which again is going to be modulated by the whatever accreting conditions we have. So now the fact that both things are generic, the existence of inner horizons and mass inflation, implies that we need to understand the equation of what are the possible outcomes, because if there is something that is increasing exponentially, it's going to have an important back reaction in the geometry. And that implies that the final geometry that we may have may be very different from the starting one that we consider. And there could be different options. It could be, for instance, that the inner horizon becomes an extremal horizon. It's not exactly a regular black hole like that. Would it be an extremal black hole because it still has two different horizons? But we can make the inner horizon extremal, meaning that it has a vanishing surface gravity. We could have a horizonless objects, situations without horizons, and many other, situations that we may not know or what we haven't figured it out yet, that we haven't formulated, but that could still be a possible solution for the back reaction problem. So I think this nonlinear back reaction of mass inflation is a key open question in order to understand in particular situations like in the figure, like in which we have Hawking radiation, for instance, that is going to pinch off these horizons. So that a geometry like this could mimic black holes for a very long time. But in a situation like that, we need to understand what happens with this nonlinear back reaction in order to really have under control the features of the geometry and what are the possible observational implications that we could have. And in case you think this is something interesting, you can read more details in the paper here, which is published in Archive, which was also essentially the report of a workshop that we had discussing not only mass inflation, but all the aspects about the geometries, different geometries that could mimic the properties of black holes. So with this, I'm gonna finish the talk with some conclusions. So just a recap and concluding. So the recap, I said recap stating that event horizons and Cauchy horizons are useful mathematically, but they are not needed in order to define objects that have the characteristic properties of black holes, like in particular, meaning that light and matter is being trapped for a certain amount of time. And actually, we have shown with a particular example of mass inflation that when we have theorems which are valid for horizons, for event horizon and Cauchy horizons, they can still be extended to finite time results that have a wider applicability. So actually, we can think about this in terms of mathematics, is that we are relaxing the assumptions in the theorem so that we are making them weaker, so that we make the theorems applicable to more general situations, while still recovering the usual cases in a certain in the adequate limit. We have shown this with mass inflation, and we have shown that mass inflation understood as a dynamical exponential buildup of mass and energy is a generic phenomenon that is associated to inner horizons and not just Cauchy horizons, because it's still there even in situations where we don't have a Cauchy horizon. And this is a strong motivation to study the nonlinear dynamics that is going to result from studying the back reaction of this inflation. And personally, I believe that this is a fundamental problem. That is, and I think that there are many interesting ways to understand and to advance along its understanding. And I think that it may significantly change our understanding of black holes in the future. So if you, we can also discuss this in the questions, or if you find it interesting, stay tuned about further developments. Thank you.
Thanks, nice talk. I have a question on the slide where you showed the exponential inflation. So this one, yeah.
Mm-hmm.
So let me understand this. Tell me if I'm misunderstanding your picture. So you have some black hole of mass m naught, let's say 10 solar mass, right? And you threw in from the exterior, say 0.01 solar masses in accretion. And at the end of it, you're getting some 10 to the 7 times one solar mass. So that's I'm just trying to understand, because both the horizons are merging. You are saying at the end of the day, in this time, in the situation where you're actually looking at dynamical evolution, the interior mass is actually affecting the exterior space-time as well. I mean, the ADM mass, which you would calculate at the end of all this, would actually be amplified by a factor of 10 to the 7 or whatever, right? This is a big change from the usual story of mass inflation, where you will never see it affecting the exterior space-time at all, right?
Yeah. So the mass. So if we didn't have the pinch of the region, right? Like the exponential behavior of the mass is clear. It's always increasing, right? And as the question that you're asking is about what happens, if I understand correctly, when we cross, right? Because it opens and then we can see this energy, right? Of course, energy has to be conserved. So we know that energy conservation is taking place in the system. And actually, so we would also, if we need to understand the evolution of the system, we would also need to understand what happens when the shell crosses, because we can also still have some phenomenon which is the opposite, essentially energies becoming negative, some energies. But I think the reason why I don't consider that to be physically, and actually, like even if I'm representing the figure like this, I think at some point this figure is not correct, or is not really giving us the correct intuition, just because the mass is increasing so much that we need to take back reaction into account. Essentially, there is a line here which is telling us whatever is being done until here, or after here, we don't really understand. So we really need to take into account this back reaction, and this is going to change the whole picture. So if we didn't take this into account, it would be the way you were saying. So essentially, we'll have the mass is increasing. At some point, this mass is released, right? And there is a huge change. But in my understanding, like what this is telling us is that we really need to take into account back reaction in order to understand the evolution after that point, because that can change dramatically the picture. The issue with that is that we need equations that, like for instance, that give us a regular black hole dynamically, and that we can understand at the nonlinear level. And that's an open problem right now. So if we had those equations, we could do the same problem, but we can analyze the same problem, but we could go beyond the linear order in order to understand nonlinearly what happens with this instability. Essentially, this is one of the key issues that needs to be understood. I don't know if that answers the question.
So Raul, yeah, that is perfect. And I had the same question that Prashant had. But let me ask you just physically. Physically, after the thing has pinched off and you go further along, one would think that the mass at infinity will go back to 1 plus 0.01, whatever fell in, right? Which means that has to come down later on. And if it doesn't, that is really a very weird result. So what you're saying is you don't know how to calculate beyond this point because it's a new problem, it's a new nonlinear problem. But do you agree that you expect this curve to then come back down to the initial value, more or less?
Yeah, I expect that once you get all the ingredients in the picture consistently, you need to have like this. You're not going to really see a dramatic increase in the mass from outside. So essentially, let's say that this dramatic increase, it's only telling you that you need to change the geometry in a radical way for it to be consistent completely. And then, yeah. So in practice, it's equivalent to what you are saying, that I would expect the curve to go down because I don't expect to have, well, it's not possible to have a violation of energy given the setup that we have. So.
Yeah, you will expect a huge amount of gravitational radiation or something. Right?
Something will come. That's the big, whatever.
But then also
very interesting.
Yeah, I don't know.
But I think we ran out of time.
Yeah. Okay. Do you have a question?
No, I have the same question. Where is the energy coming from?
I'll get it. Yeah, wonderful.
Yeah.
Thank you.
Thank you.
Thank you.
I wonder if that's something kind of analogous to magnetic reconnection, that
Yeah.